And today we're going to start chapter 4, which is heat transfer. Now, does anybody have any questions or comments about chapter 3? Alrighty then. Well, let's do heat transfer. Okay, well, the number one thing that we need to remember about heat transfer is the signs in these mathematical problems matter. Because if something turns out to be a negative sign, that means that heat has left the object. And if there's a positive sign, heat has been gained in the object. All right. Now the good thing about chapter 4 is there's simply one equation. All right. And here's the equation: Q equals mc delta T. Now, as you can imagine, in chemistry we are concerned heavily with heat, with energy, because most chemical reactions either heat up or cool down. In other words, there is some sort of a temperature change. Not all of them, all right? Some chemical reactions, known as chemiluminescent reactions, they give off light as their form of energy, all right? But most of the time, a reaction will heat up, most of the time. There are reactions that cool down that are very well known and common. So, that's what we're talking about here with this Q. That is our energy, all right? Now, reading the back of a pack of M&Ms or a soup can or whatever, that energy is given in calories. All right, it's actually something called a kilocalorie, right? The United States version. But in chemistry, the international version of that is something that's a J for joules. All right. So first off, this Q term is energy. If it is negative, heat has left whatever object we're talking about. If it is positive, that means heat has been gained by that object. Second thing is mass. All right. Now that's pretty self-explanatory. All right. If we're heating up a thing of water, you would naturally think that the more water you have, the more energy that it would take to heat it up. Or the less water you have, the less energy it would take to heat it up. So that's kind of a common sense thing. Now, this delta T, anytime you see the symbol delta in a math equation, not a chemical equation, but a math equation, that means change in. And it's always the final minus the initial. Now, we have to be anal retentive about that. Why? Well, what would be the only difference in the numbers if you did initial minus final? It'd be negative or positive or whatever. Okay, the sign change. Now that's extremely important because negative numbers tell us that the reaction is going to be heating up, right? Energy is going to be leaving the system. Where positive numbers tell us that the reaction will be cooling down. So if you run in a chemical plant, that's very important to know. You can't get all screwed up about that. So it's final minus initial, always, always in science. There's one example I know of in nuclear physics where that's not the case, nuclear binding energies, all right? But unless you're doing that, final comes first. Okay, so now we have a new equation here, right? Final temperature minus initial temperature. Now what is this C deal? Well, this C is the specific heat. You see, every single thing has a specific heat. Now things like metals, all right, that tend to conduct heat and electricity well, they tend to have very low specific heats. Like, for an example, the specific heat of iron is 0.473 joules per gram degree centigrade. Now, what do you think about a piece of iron? Do you think that's going to heat up quickly or not quickly? That's going to heat up relatively quickly, right? That's a pretty low number. Now, if you take something like gold or lead, you're looking at like a 0.1. Those are extreme good conductors of heat and electricity. Now, what about water? Okay, now water specific heat is 4.184 joules per gram degree centigrade. All right. Now, what do you think about water? Do you think that's a good conductor of heat or not a good conductor of heat? What's that now? Not a good conductor of heat, right? Think about it. Your body is mostly water. And if you step outside, all right, and nothing but your underwear on, and it's 32 degrees outside, freezing, or 20 degrees outside, are you going to freeze just like that? I mean, absolutely not, right? I mean, it's actually going to be cold. It's not going to be comfortable, but I'm talking about, will you absolutely freeze? No. It will take quite some time for you to get cooled down. Now, what about a piece of iron? If you put that outside in the snow, how long is it going to take for that to get cold? Not long at all, compared to a body, or compared to water, a tub of water, right? Certainly water is going to freeze. It's going to take longer for water to get to 32 degrees than it would be this piece of iron. Same way it goes here in Florida, right? It's 102 degrees outside, what have you. You can be outside and not overheat. Why? Because water here has a wonderful insulating property. That's one of the many reasons that water is inside a human body, is it helps to keep you temperature regulated, right? I mean, certainly everybody's heard on the news, drink lots of fluids a day, temperature is going to be over 98 or what have you. Why? Well, they want you to keep this insulative ability going. And I don't know if any of you guys are from up north either, but if you're camping out and it's frozen snow on the ground, you got to drink too. All right? That hydration will help you keep those fluids in the body. So that's the equation there about Q equals MC delta T. So let's work an example. I want to know how much energy, okay, will be required, okay, to raise the temperature of 128 grams of water from 28 degrees centigrade up to 98 degrees centigrade. Okay? So here's what I'm going to do. I'm going to take a pot of water that just happens to randomly have 128 degrees in it. I am going to put that on top of the stove and I'm going to cook on it. All right, so here's a little picture here. We got this beaker of water and I am going to place it onto the stove eye here and start putting heat into the system. So I want to know how much heat is going to be required to heat up that much water. Well, the first thing you're going to do is write down your equation. Q equals MC, final temperature minus initial temperature. Okay, we're looking for heat, right? We're looking for the energy. So the thing's already been algebraically manipulated, right? That's easy. It's the thing on the left-hand side. All right, so what is the mass here? 128 grams. Okay. Now, what is the specific heat of water? Well, I already told you what it was. It's 4.184. Now, how would you know that? You would look it up in a table. And if I'm not mistaken, your specific heat table is on page 43 of your textbook. Now, don't nobody panic until I look that up. That's wrong. It's not on page 43. It is on page 73. Okay? The specific heat table is on page 73. Now, would these numbers be given on a test? Naturally they would be, right? Back there on the back page, whenever you take your exam on Friday, there's going to be conversion factors for you. There's going to be a periodic table there. There's going to be all sorts of information. Now, I'm not going to put it beside the problem. Please use this number to work this problem. All right, you'll have to know we're looking for the specific heat of water. Now, pardon me, the specific heat of water is 4.184 joules per gram degree centigrade. All right. Now, what's the final temperature? 98 or 28? 98. Minus 28. So will this number be negative or positive? Positive. That's what we want, right? Because remember, in thermodynamics, a negative number means heat is leaving. Now, is heat leaving this water? Absolutely not. You got it on top of a stove eye. Naturally, heat's not leaving the water. Heat's going into the water. So this positive sign here is what we would have expected. All right. So, okay, so that's going to be 70 there on the right? So it's 128 times 4.184 times 70 will equal 37,488.6 joules of energy is what is required to raise the temperature of 128 grams of water. Now naturally, as the mass of water goes up, the more energy you would need to impart into this system. All right. Now some of you guys that may be going to some college somewhere and doing engineering, you might have heard of thermodynamics part 1, 2, and 3. All right. And it gets extremely complicated. Look at all the assumptions we're making. We are saying that this heat goes into that water, right? Now do you think that's really what happens or all that's happening? Absolutely not. You walk into the kitchen, you feel heat, right? Where's the heat come from? That stove out. So all that heat ain't going into that water. All right, some of it's imparted into the container, some of it's involved in evaporation, all this drama. Okay, how are we doing? Good? All right, you guys ready to work a couple? Maybe? All right, well, why don't I then let you see how they are typewritten, let you work a couple, and then I will come back and work them on the board for you. Okay? So here's what I want you to do. Go ahead and work number 17 and 19. All right, number 17 and 19 on page 78.